Hey guys, it's IBM taking you through magnetic fields and electromagnetic induction. These are past paper questions of 9702. This is physics paper 4. I think this is going to be part 22. That is part 22. Explain the use of a uniform electric field and a uniform magnetic field for the selection of the velocity of a charged particle. You may draw a diagram if you wish. I think we have also answered this question earlier on, so just repeating it here is just emphasis. In the previous video, in one of the videos when we answered this similar question, we said you can drawing a diagram makes life very easy. For example, I must show a uniform electric field, which means I have to draw parallel metal plates. So let's just assume these are the plates. And I could say the upper plate is positive, the bottom plate is negatively charged. So then let's say the particle enters from this side with a velocity, let's say it is v. Let's say the particle is positively charged. The positively charged particle is easier to deal with when it enters the magnetic field. So if the particle is positively charged, of course it means that the electric force is going to be downwards. The force due to the electric field on a positively charged particle is going to be downwards. So by all means, I should make the magnetic force to be upwards. So the magnetic force must be upwards so that the particle can go through the field, the crossed field, without being deviated. So for the particle to go through without being deviated, the magnetic force is going to be upwards. So F due to the magnetic field should be upwards. And how am I going to make that possible? I'm going to introduce a magnetic field into the page so that by Fleming's left-hand rule, when the force is upwards, the second finger is pointing towards the right, the thumb points into the page. So I'm going introducing a magnetic field which is into the page. So this one is going to be magnetic field into the page. So that is the magnetic field into the page. Of course, the plates just indicate an electric field. I don't need to explain that. So for no deviation, the magnetic force Fm should be called the electric force, which I'm calling Fe. That is BQV should be equal to Q times E. And that means the particles whose velocity V equals to E over B will pass through undeviated. Now by just doing this, I could have almost all the marks without even writing anything. But if I want to write, then I could write and say that the electric force, the electric and magnetic fields are perpendicular to each other, as you have seen. The electric field is downwards, the magnetic field is into the page, that is perpendicular to each other. So the electric and magnetic, the electric and magnetic fields are perpendicular to each other. And so the velocity of the particle and are perpendicular to each other and to the velocity of the particle. Into the velocity of the particle. So you notice electric field is downwards, the velocity of the particle is to the right, magnetic field is into the page. Okay. The fields are such that the electric and magnetic forces on the particle act in opposite directions. The fields are such that the electric and magnetic forces act on the particle in opposite directions. In opposite directions, the fields are adjusted, so we are going to adjust the field, or the fields should be adjusted so that the forces are equal. The fields are adjusted so that the forces are equal and particles with the speed v equals to e over b, particles with the speed v equals to e over b are selected. Where E is the electric field strength and B is the magnetic field strength. Okay, so when you write the three statements, you don't even need to draw a diagram, but when you draw the diagram, you can just write one statement that the particles whose speed is equal to E over B are selected. Ions, all of the same isotope, are traveling in a vacuum with a speed 9.6 times 10 to the power of 4 meters per second. The ions are incident normally on a uniform magnetic field of flux density 640 milliteslas. Because they are incident normally, it means if the field is perpendicular to the direction of the velocity, then they experience a force. The ions follow a semicircular paths A and B before reaching a detector as shown in the figure. Data for the diameter of the paths are shown in the figure 6.2. The ions in path B each have charge positive 1.6 times 10 to the power of minus 19 coulombs times the mass in U of the ions in path B. So you notice that the path is a circular path, which means that the magnetic force provides centripetal force. So I would say magnetic force provides centripetal force. The magnetic force provides centripetal force. So I'll just equate B QV to m v squared over r. This implies that m equals to b qr divided by 1v, and we can substitute. B was 640 milliteslas, so that is 640 times 10 to the power of minus 3. Q is 1.6 times 10 to the power of minus 19. The radius of path B, diameter is 6 centimeters, diameter is 12.4, so the radius is 6.2. So the radius is 6.2 times 10 to the power of minus 2. To change it to meters, Then divide by the speed of the particles, which speed was 9.6 times 10 to the power of 4. So from the calculator, we have 640 exponent minus 3 times 1.6 exponent minus 19 times 6.2 exponent minus 2 divided by 9.6 exponent 4. So this is giving us the mass as 6.61 times 10 to the power of minus 24. So this is 6.61 times 10 to the power of minus, is it 24? 26. But this is in kilograms. We want the answer in unified atomic mass unit. So the mass is going to be 6.61 times 10 to the power of minus 26. Divide this by 1.66 times 10 to the power of minus 27. I'll just divide this by 1.66 exponent minus 27. So that is 39.8, which is approximately 40. (39.8 U). This is approximately 40 U. So the answer here is going to be 40. Suggest and explain quantitatively. Quantitatively means you need a number, or you need to be very specific with the quantities. Quantitatively, a reason for the difference in radii of the paths A and B. So why could there be a difference? They are entering with the same speed. So B QV is equal to mv squared over r, or m equals bqr over v. They are entering with the same speed. They're entering the same magnetic field. And if they're entering the same magnetic field, there are only two possible reasons. So I'm going to make Q, I can make Q over M the subject. So Q over M is going to be equal to V divided by R times B. Now that V is constant, B is constant, it means that Q, charge to mass ratio, is directly proportional to 1 over R, or is inversely proportional to R. So one I could say that Q, charge to mass ratio, is inversely proportional to R, and since radius for B is twice that for A. Now saying twice, I'm being quantitative, is twice that for A, then the charge to mass ratio for A must be twice, is twice that for B. Because charge to mass ratio is inversely proportional to radius, and the radius of B is twice that for A, it also means the charge to mass ratio for B is half that of A, or the charge to mass ratio for A is twice that of B. So ions in path A, have the same mass, but twice the charge, of ions in path B. So the ions in path A have twice, because these are all ions, all of the same isotope, are traveling in a vacuum without speed. The ions are incident normally on a uniform magnetic field as shown there. So because charged mass ratio is inversely proportional to the radius, and we are seeing that the radius of path B is twice that of path A, it suggests that the charged mass ratio for A is twice that for B. So if the mass of the ions is the same, then the charge of ions in path in path A should be twice the charge of ions in path B. In other words, we know that charge is inversely proportional to R if the mass is also constant. So the charge for ions in path A should be twice that of ions in path B. Suggest an explanation for each of the following observations. Two wires are laid side by side and carry equal currents I in opposite directions. So when wires are close to each other, the magnetic field caused by the magnetic field around the one wire is actually in the region of the second wire, or each wire sits in the magnetic field of the other. And because the currents are in opposite directions, if we were to use Fleming's left-hand rule, the current of each wire is perpendicular to the magnetic field due to the current in the other wire. By Fleming's left-hand rule, each wire experiences a force due to the other wire. So the question is, the total magnetic flux density due to the current in the wire is negligible. Two wires are laid side by side and carry equal currents, I in opposite directions as shown. We want to suggest an explanation for each of the following observations. Two wires are laid side by side and carry equal currents in opposite direction as shown in the figure. The observation is that the total magnetic flux density due to the current in the wires is negligible. In other words, just saying B is negligible. Okay, so the total. So we know that the magnetic fields, the magnetic fields due to the current in each wire are equal, because the current is equal, but because the currents are in opposite directions, the magnetic fields are also going to be the opposite directions. So the magnetic fields due to the current in each wire are equal in strength. Let me say equal in strength. They're equal in strength. In other words, they have the same flux density, but are in opposite directions. Because the currents are in opposite directions, when you use the right-hand grip rule on each wire, you notice that the magnetic fields are going to be in opposite directions. But because the currents are equal, the magnitudes of the magnetic fields are equal. So because they are equal but they're in opposite directions, we can think about the total as being, because magnetic flux density is a vector quantity, the resultant is the algebraic sum. So they cancel out each other since they're in opposite directions. The fields cancel out each other. Cancel out to give 0 or negligible resultant field. The fields cancel out to give 0 or negligible resultant field. I want you to note at this point that the direction of the magnetic field around each wire is determined by the right-hand grip rule. So imagine the right-hand grip rule on the top wire, it will give a magnetic field in one direction, and the right-hand grip rule on another wire will give magnetic field in another direction. So these fields, because they are equal in magnitude and opposite direction, they will cancel out each other. An air-cooled solenoid is connected in series with a battery as shown in the figure. The observation is an ion core is inserted into the solenoid. An e.m.f that opposes the e.m.f of the battery is induced in the solenoid. As an ion core is inserted, so inserting an ion core is equivalent to increasing the magnetic flux in the solenoid. And this change is going to induce an e.m.f in the core, and as a changing flux in the core is also going to cut or is going to thread or to spread um, or to cut through the turns of the solenoid, and by Faraday's law an e.m.f is going to be induced in the solenoid. Of course, by Lenz's law, this e.m.f opposes the battery e.m.f. So an e.m.f that opposes the e.m.f of the battery is induced in the solenoid. So inserting the core causes an increase. Remember, the ion core concentrates the magnetic field. So inserting the core causes an increase. An increase in magnetic flux in the solenoid. Or around the solenoid. So inserting the core causes an increase in magnetic flux in the solenoid or around the solenoid, and a changing magnetic field is induced in the core, and a changing magnetic field is also induced in the core or spreads to the core. A changing flux in the core, a changing magnetic field in the core cuts the turns of the solenoid or threads the turns of the solenoid. A changing flux or magnetic flux in the core threads stroke cuts the turns of the solenoid. So inserting the solenoid has induced a magnetic field in the solenoid, but this is changing because the magnetic field causes the magnetic flux to concentrate or to grow. This changing flux in the core is going to again spread or is going to cut the coils of the solenoid or the turns of the solenoid. And by Faraday's law, so by Faraday's law, an e.m.f is induced in the solenoid again, but this e.m.f induced in the solenoid is caused by the changing magnetic flux in the core, not in the solenoid. So by Faraday's law, an e.m.f is induced in the solenoid due to the changing flux in the core, but by Lenz's law, by Lenz's law. This EMF is such as to cause effects that oppose the change producing it. In other words, this EMF opposes the battery EMF. This EMF opposes the battery EMF. As simple as that. It's quite abstract, but that's the truth. A particle has mass m, charge positive q, and speed v. State the magnitude and direction of the force, if any, on the particle when the particle is traveling along the direction of a uniform magnetic field of field strength G. So the particle, state the magnitude and direction, if any. So a particle has mass, so the force is given by m times g in a gravitational field. The direction is towards the center or acting in the same direction of the field. So this one acts along the direction of the field. Acts along the direction of the field or along the direction of the motion. So for a particle in a magnetic field, the force is mg, which acts along the direction of the field, normally towards the center of the larger mass. Then the magnetic field of flux density B. Of course, the force due to the magnetic field does not depend on the mass, but instead it depends on the charge. However, they said if any on the particle when the particle is traveling along the direction of the field. If the particle is moving parallel to the magnetic field, then the force is zero. Fleming's left hand rule does not apply. So in this case, the force equals to zero. The force equals to zero because magnetic force only acts when a charged particle has a velocity component. Perpendicular to the field. Perpendicular to the field. So if it moves parallel, so if it moves along the field, it has no perpendicular component. So it should be moving at an angle to the field so that there is a velocity component perpendicular to the field. Two charged horizontal metal plates straightened in a vacuum produce a uniform electric field of field strength E between the plates. The field strength outside the region between the plates is zero. The particle in A enters the region of the electric field at right angles to the direction of the field as illustrated here. So we have a uniform electric field. A uniform magnetic field is to be applied in the same region as the electric field so that the particle passes undeviated. Okay? So the particle is positive and the electric field is downwards, so it means the force due to the electric field is also downwards because for a positively charged particle, the electric force is always in the same direction as the electric field. State and explain the direction of the magnetic field. So because the electric force is downwards, For no deviation, the magnetic force should be upwards. They should be equal but opposite. And then using Fleming's left-hand rule, for the positively charged particle, the second finger points in the direction of the particle, the thumb points in the direction of the magnetic force. You notice that the first finger will point into the page or into the plane of the page. Therefore, I'll simply say that the force due to the magnetic field must be upwards. I think this is the third time I'm answering a similar question. The force due to the magnetic field must be upwards, since the electric force is downwards. Because the electric force is downwards, remember I said the electric force on a positively charged particle is in the same direction as the field. Because E is showing that the field is downwards, the electric force is downwards. So for no deviation, we need an equal but opposite force. So the magnetic force must be upwards if we introduce a uniform magnetic field. And by Fleming's left-hand rule, the magnetic field must be into the plane of the paper. So it must be into the plane of the paper, as I've illustrated with this Fleming's left hand. Derive with explanation the relation between the speed v and the magnitude of the electric field strength, and the magnetic flux density B. So for no deviation, the magnetic force, magnetic force should be equal but opposite to the electric force. And if that is true, I would just simply say BQV is going to be equal to Q times E, which implies that V is equal to E divided by B. So the explanation, if there is no deviation, the magnetic force is equal but opposite to the electric force. A second particle has the same mass m and charge positive q as that in B, but its speed is twice v. So if the speed is changed, and remember the speed affects the magnetic force, so it means the magnetic force is bq into 2v. So the magnetic force has been doubled, yet the electric force has not changed. The particle enters the region between the plates along the same direction as the particle in B. On figure 6.1, sketch the path of the particle in the region between the plates. So now that the speed has been changed, the magnetic force, I've said the new magnetic force is going to be BQ into 2V, which is twice BQV. So now the magnetic force is greater than the electric force, because initially they were equal. Now the magnetic force is greater than the electric force because the speed has been doubled. So that means the resultant force is in the direction of the magnetic force. Therefore, the curve should be, the particle will be deviated towards the upper plates. So I will draw a smooth curve here. I no longer need this because I already know that the magnetic force is upwards. So I'll just draw a smooth curve. Of course, when we come out of the field, you put a ruler and draw a tangent to the curve, because outside should be a straight line. Okay, so the curve is going to be upwards. Okay, that is part 22. See you in part 23. Bye bye.